How do I move to? Well, thank you first of all for staying for our last talk today. I know this can get tiring on the conference days, and please feel free to interrupt me with questions if you have any. So yeah, I wondered a little bit. So I got this invitation, and I saw the topic is flat bands or hidden correlation flat band side. And I was at first I was like, oh my God, what am I supposed to talk about? Because we don't do that. We do a little bit of flat band work, and I get to this in the end, but it wasn't like immediately something to our topic. So what I thought I'll do is I'll just give a little bit of an overview, not actually what we do. This is just one slide, but about how we think. So this is our group here in the chemistry department. This is a little walk from here, 10 minutes walk. And we like to think at the interface of chemistry and physics, and specifically we like to leverage what we know from chemistry to have an impact in physics. And we do it in the area of topological materials, 2D materials, and what I like to call complex collective phenomena, which I mean magnetism or charge density wave compounds or anything, some collective aspect to it. But I mean, a lot of our work, I mean, you can focus on results and what we get, but a lot about our work is actually thinking about work like chemists. And so this involves a lot about thinking about bands and band structure. And so I want to talk a bit about how chemists make an understanding and logic of this. Basically, how do we link this triangle of things? So we link a crystal structure to a band structure, a crystal structure to properties, and properties to band structures. You might hear maybe be a little bit familiar with this lower part. We're really trying to involve the crystallography aspect also in our research. And so part of this will be about flat bands. This will come more at the end. Other parts will be about the opposite of flat bands, which is steep bands. So let me talk a little bit about general, what can we learn from an electronic structure? So if you see simple electronic structure, there's some properties you can simply infer from it. For example, if you have steep bands like you see here or here, you can infer that's very likely that your material will have a high mobility. So if you look for highly mobile electrons or any kind of application physics you look for, steep bands are your friend. Flat bands you're interested for because there is a potential of having correlations. Not every flat band will host correlations. We'll talk about it a little bit also. But if you're interested in looking for correlated compounds, maybe for superconductors, the flat band might be an indication, right? So there's lots of things to be looking for those. And then another thing is that the field of topology brought us is if there's a band inversion, then it's a good you have a good shot that you will have a topological material. So you can also infer directly from the band structure properties for that. Okay, great. But how do we get from this crystal structure? And for this, actually, we have to think more than just crystal structure. We have to think about chemical bonds. So here's an example of sodium chloride. This is a strongly ionic bond. And whenever we have a strongly ionic bond, chemists intuitively know we will have probably pretty large band gap in the material. So we already, just from knowing like this is very ionic, we know part about the band structure in the compound. Right? And so sodium chloride is an example. Although you wouldn't initially consider this for anything with steep bands or high mobility because you know it has a large band gap. However, you shouldn't disregard it for topology because I recently learned it can have some corner states or something, and everything becomes topological now. But if you think about it of the classical way of normal band inversion, then it's maybe not that interesting. But then there are other structures where you have more than just ionic bonds. You have actually covalent bonds, like real chemical bonds in your system. And if you have those, then the description becomes less simple, but also you can use a lot of chemical intuition to understand what these kind of bonds will do to your electronic structure in the system. And this is actually what we are interested in the group in understanding. For this, we need to talk a little bit first about how chemists think about band structures, because a lot about what is bonding and bonds have to do with band structure is given from a chemical viewpoint about band structure. And I like to show the slides of the contrast and how we think, because as chemists, we really don't like to write down Hamiltonians. And some of us do. One of the chemists sitting here in the audience that does, but many of us don't. And we think about stuff very much by just drawing orbitals. The chemists like to draw orbitals and therefore think about bonds and bonding and how they overlap, and we can extend it to band structure. And there's a person, the chemist, who maybe not many of us know, you know, it's Roald Hoffmann, who pioneered, really, he wrote such beautiful work that I read as an undergrad that really brings band structures close to chemists and connects the words between condensed matter physics and solid state chemistry. Look up his work if you're interested in how chemists think. Like, he changed my life in an undergrad when I read his work, and in 2018 I finally got to meet him, and thank God I'm still have the fortunate to discuss with him, because sometimes you can really learn a lot of things from this pioneer. So all the credit of what I'm going to tell next goes to Roald. This is not our work. So this is what Roald taught us in this really, really beautiful paper here, Pinch's highlights. So this was written shortly after I was born, so it's a long time ago. Nothing new, but it still works beautifully to understand quantum materials today. So the simple idea is, okay, if you put the simple tight binding model into a block function, and you could do the math, but instead of doing the math, you can just draw orbitals. This is a linear chain of hydrogen, so you just worry about s orbitals in phase, and you will see that at the gamma point, when you get this equation, all your orbitals will be in phase. So this is a very bonding molecular orbital which responds, if you think in molecular orbitals, which means the band here has to be low in energy, because whenever something is bonding, chemists know it was energetically preferred. And if you extend this out in K space to the edge of the Brillouin zone, you will have alternating phases of your orbitals, and you have the most anti-bonding phase, and therefore this will be high in energy. And just by knowing this, just by drawing this, you can draw a band, when you know this follows a cosine function for a linear chain of hydrogen atoms. Don't need to write down any equations. You just look at, you know, basically from looking at the equation once, that everything what happens throughout your K space throughout the Brillouin zone is that your orbitals switch phase and decrease the number of nodes here. So you start from very bonding, you go to very anti-bonding, and you learn to get this type of a band structure. The other thing that you know is that this is an anti-bonding part of a band. So if you start taking electrons out here, you will shorten the distance, because you will get more overlap between the atoms, and you will make this more bonding, you will steepen the band, and you will get a more bonding interaction. You can continue this kind of really simple model if you consider a molecule of hydrogen. So this is still, all of the atoms have the same distance, but you know, enlarge the unit cell to consider that in the end, a hydrogen atom has a hydrogen molecule has two atoms, so you double the unit cell. And what you have to do then is you have to put a molecular orbital of one phase and the bonding MO and an anti-bonding MO at the same point in the gamma phase. Chemists know this really well for a band structure. And so you will start with a very low energy bonding orbital here and a very high energy anti-bonding orbital here, both at the gamma point. And then these will move around by switching phase to the K point, and you will see that they actually become degenerate here at the K point. And so this is the band folding you might have heard about, right? From here to here, you just fold the band structure, but it actually makes a lot of sense if you draw out the orbitals that this is happening. If you then let the hydrogens form molecules, like we all know they like to do, and you form a bond, which is also called the pious distortion in 1D, you reduce the distances here. And if you do that, this interaction here becomes bonding, and this one actually becomes anti-bonding. From the distances, you will open up a band gap here. And you all know hydrogen is an insulator, so that's what you expect. Okay, so very easily, just drawing orbitals and thinking about overlap if something is bonding or anti-bonding can explain to you concepts like a pious distortion in 1D. And so, as I said, this is in our work, but this influenced a lot about how we think about materials today.
So what's the difference between these two? Because
yeah.
are similar.
Yeah, so yeah, it's not super. You see here, this distance is shorter and this distance is longer, and here they're all equally distant. So that is the difference. And so if here at this, it's really, yeah, it's not great to see. I have to update the figures at some point. So here, these are degenerate, right? Because you have two white, two black, two white, two black spheres, and here also over the boundary, but they're equally distant, right? But here, those two white spheres are closer to each other than the black ones. Yeah, it's sorry. And then here they're further apart, so that they're not degenerate anymore in energy. Yeah, but thank you for asking. So just when I talk so much about bonding, I just want to put this slide real quick. Bonding, what we describe as a bonding orbital or overlap between things, is really when you have a positive overlap integral here, and you can have an overlap between your electrons. Anti-bonding means there's really no overlap, it's negative. And there's also something called non-bonding, and we'll get to this later, when you have no overlap, so there's neither bonding or an anti-bonding interaction, like there's no overlap at all. Integral is 0 here. if you define the overlap integral. And you might think maybe this is cool for flat bands. We talk about later why it's actually not, but this is also a type of interaction chemists think about. So these are the three main types of things for this. Okay, so I want to talk a little bit about, once we know this and we understand with this hydrogen, how we can really simply understand graphene. I mean, I guess you think graphene is already simple, and I think many of you in the room wrote down the tight binding model for graphene once, and I'm sure you can all solve it. But like the qualitative idea about the properties of graphene, you can just by putting by putting a pencil in your finger and sketch out the orbitals, and you don't actually need to write down the tight binding model. And so this is, if you just say, okay, we have one carbon atom in graphene that repeats, and it has 3 sp3 bonds. We ignore those because those are filled electron shares that go away, and then we have a half-filled pz electron, so a pz orbital here, which is left and which forms the pi bonding. But it's half-filled because we have 1 per carbon. So intuitively, a chemist, like ignoring the geometry for now, just sketching one band would sketch something like that, which predicts accurately that graphene is metallic, but it doesn't accurately predict the Dirac cones and all the things you care about the band structure. However, we can make a very simple, let's say, straw man's argument. We can say, obviously, okay, you guys all know, I don't need to tell you this, graphene has 2 atoms per unit cell, so let's just do the same thing as we did with hydrogen and fold it. And now we get the folded band structure, and we know the upper part is the anti-bonding part, right? So it's the pi star band, this is a pi band. The lower part is the bonding part. As we learned this word. And so if we sketch this out to a second variance of gamma star, we see how we get a crossing. We don't get the exact tight binding band structure that you would get with the model, but we get a Dirac crossing, and we get a band inversion. Clearly, that your pi star will move below your pi if you do that. Okay, so you can understand the very simple principles of graphene just with that super qualitative argument, which is that there must be a Dirac crossing, and then there must be a band inversion in the system. And so that question lets us understand why actually, because we did the hydrogen argument here, doesn't graphene go for the next step and like now form bonds and does a Pius distortion and gaps everything like it did in hydrogen? So why do we stop actually at this point? And so the reason for this from a chemical standpoint is that we have the perfect delocalization of the p electrons here in the system. We like to draw them as rings. You might have seen a benzene molecule once the ring, which just does it. Graphene does the same thing as benzene. But if you were to localize these bonds, there wouldn't be equidistance anymore, and we would get a normal band gap. Or if we do anything else to mess with these bonds, let's say different electronegativities like boron and nitrogen, we get boron nitride. That's a massive band gap, no band crossings, all open. We attach hydrogen in one, actually we start to buckle it. We break this perfect, what is called sp2 hybridization here. No, we get a band gap, right? No band crossing anymore. So our argument back then must be, okay, it must be this delocalization that causes this band structure in graphene. And I know you like to point out in the physics community that it's the perfect hexagonal symmetry that does it, and the lattice. And just my point is, it's kind of the same thing, because if you localize these bonds, the bond lengths become different, and you also would break the symmetry, right? So it's a chicken of an egg thing. What is what? Like, is the symmetry the cause, or is the delocalization the cause, right? So I like to talk about this in case of delocalization. So the argument is, if I have this delocalized structure, I have an inverted, nice graphene band structure. If I do not have this, I will have an uninteresting normal gap band structure. So then my question, of course, was, okay, when can I have delocalized bonds? So let's revisit all the types of bonds we had. We already briefly meant ionic bonds before, like in sodium chloride. It's not delocalized at all, very localized, and will have a band gap. You can have strong covalent bonds like in diamond or silicon. It is pretty localized between these atoms. Like each 2 electrons will sit between 2 atoms and bond these, also sometimes called 2 electron to center bond. And it's also going to be just insulating. Or you can have delocalized bonding that we just find out, and apparently you get a more better bond structure. But there's some problem with this, because this type of delocalized bonding that we know from graphene is very limited to carbon chemically. There aren't many other elements that have this kind of pi bonds. Actually, it has been a chemical challenge often to repeat carbon chemistry with any other elements. And if you can do this with like 2 or maybe 3 chains of atoms, then you're a chemistry hero, but forget doing it with like a whole layer like graphene. And there's a good reason why early predictions of really cool topological properties in stannine, silicene, germaniums were never be realized as freestanding material. So we had to think about a different type of bond that is still delocalized, but not pi electron based, that we can have in other materials. And so to find this, we went actually back to molecules first, because chemists, unfortunately for us as solid state chemists, a lot of chemistry lives in molecular space, and sometimes very helpful to go back and understand what the molecular chemists have understood to get conclusions. And so there we realized molecular chemists have known for really a long time, I don't actually know, maybe 100 years, maybe longer, about molecules that they call hypo and hypervalent. I'll tell you in a second what this means. These are molecules like BH3 and PH5. And before we discuss everything, I come back to this slide in a second. Let's just remember the elements that are important here, boron and phosphorus. And we look here in the periodic table very quickly what they are and what they're supposed to do. So boron is here and has 3 electrons. So it has 2 s electrons, 1 p electron here. To be happy and satisfied in its valence shell, it wants to go all the way to 8. Okay, this is like the goal of everything up here is get 8 electrons. Okay, helium wants 2, hydrogen, helium want 2, all of those want 8. Here they want 18 if you count the d electrons, but they always want to go to have exactly the same amount of electrons like the noble gas. That's the basic concept. Now you're chemists, all of you are chemists. That's the basic, like all of chemistry basically is based on that idea. And boron has only 3. So and phosphorus, that we talk about later, has 5. So if you give hydrogen to boron, you can attach exactly 3 hydrogens to it, and then it's done. Yeah, because it doesn't have any more electrons to bind another hydrogen. But only with 3 hydrogens are bounded, even if you count both of these electrons to the boron, it will have 6 and not 8. So it doesn't have a filled valence shell. And that means it's called hypovalent, 2 little valence electrons. And what it does to get rid of this electron deficiency is it forms a dimer where it uses a hydrogen atom here to bridge. And so it forms these, which are called, I don't kid you, banana bonds. They're really called like that. So it forms banana bonds. Some people also like to call them 2 electron free center bonds, in which 2 electrons are delocalized over these free centers or atoms, boron, hydrogen, boron. So here we have some delocalization. It's not pi based in a molecule about more atoms. And so you can also have this as hypervalent. So remember the phosphorus had 5 electrons, so it can now grab 5 fluorines. The fluorines all happy, they only need 1 extra electron. But now it has 10 electrons around its valence shell. That's too many. It doesn't want 10, it wants 8. So what it does to get rid of this excess, so it's hypervalent, is that 4 of those electrons will delocalize here along this axial line of the molecule, so that at a given time, there's always only 8 electrons around the phosphorus to make it happy, and the other ones run around here. So again, you have delocalization that is not pi-based in a molecular system, and the question was, can we take advantage of this type of delocalization that happens whenever systems have either too little or too many electrons to be satisfied? Can we have that in more than 1 dimension or in a solid system? And then you can see what the effects are on the band structure if it's related to graphene. And so again, Roald Hoffmann, who I showed earlier, answered the first question to us is, can we have these things in a solid system? Because he wrote a beautiful paper in 2000 where he said, hey, there are compounds. These compounds have linear chains of antimony. So they're not freestanding, they're in a crystal. Or they have square nets of antimony. And if you count this, then what is called the Clem's concept is violated, which is a fancy way of saying the counting to 8 doesn't work. And so he said, in order to understand it and put it in chemical terms, we have to classify these systems as hypervalent. Okay, let's understand for a square net why is this hypervalent. Okay, so such a square net of antimony can exist in a crystal. Because it exists in a crystal, it's actually antimony minus here. So there's some positive cations to charge balances. If you look here in the periodic table, here's antimony. We have 5 electrons. This is antimony minus, so we have 6 electrons with a negative charge. And if you put 6 electrons on a planar square net, you cannot count to 8. If you put a lone pair on top of this antimony, you would buckle it. And so the only way you can put 6 electrons here is if you understand there are too many and they're hypervalent and they need to be delocalized. You can also think about it, it's something like an antimony minus with 6 electrons, so it should act like an element here in this row, which has also 6 electrons. So let's look at sulfur, for example, that likes to make zigzag chains, where it makes 2 bonds, 2 lone pairs, and doesn't like to form a square net. And so this contrast of a delocalized square net to this kind of thing is similar like in graphene, where we said, okay, if in a perfect hexagonal symmetry, we have delocalization, we get the Dirac cone, but if we would localize electrons, we would get distortion. Similar to here, we wouldn't get one. And so here's a more physics picture of understanding why there need to be delocalized bands in this square net. This is electron counts. That is, if you put the orbitals of antimony into D4H symmetry, like you have in a square net, this is the splitting you get. And if you fill it up with 6 electrons, you see you will get a half del pxpy manifold. So if you don't want to have an antimony magnet, which I've never heard about existing, you will have to have a delocalized half del band here. You can then also go ahead and actually write down a tight binding model if you're chemists like me, the friend in the physics community who does it for you. And then you get a beautiful tight binding model here with steep Dirac crossings, and you see how the px and py orbitals cross it inward. So you have Dirac crossings and you have a band inversion, unlike graphene that is happening here, not at a point in k-space, but at the high symmetry. Yes?
Very naive question. Why silicon is not exactly like carbon?
Well, so in silicon, is a good question. In silicon, the d orbitals are closer in energy from the p orbitals than in carbon. So if you make any silicon hydrates, like analogs to carbon hydrates, there are d orbitals in the vicinity where any kind of oxygen, water, and the environment can attach. So any silanes like SiH4 or S2H, I can't count 10 or whatever this coming then, will react violently with air and water, and it's very hard to be stable. And then with double bonds, which you would need for any kind of graphene things, there's actually something called the double bond rule, which says only the second row on the periodic table where carbon can form stable double bonds. And so people have made molecules with silicon-silicon double bonds or even triple bonds, but you need to put a lot of steric stuff around it so that this bond is protected to be attacked from anything else to stabilize it. So you cannot just have it like that.
So you would like to keep the first row, like the p orbitals.
Exactly. So the difference is that you have s and p orbitals, and then there's a long energy gap for d orbitals to come in the first row, and then the other ones, the d chemistry starts mixing in and messes everything up basically. Okay, great. So yeah, so you get this band structure from a tight binding model, and if you calculate the DFT calculation on a compound with such a square net, you see that it's pretty related. As I was saying, this is a little bit different from graphene because you have the crossings not at a symmetry point, but at a line, which means they form actually nodal line in the Brillouin zone. So these are called nodal line semimetals. But like for us, chemically, they're analogs to graphene. Okay, they're a little bit different, of course, because of the. So I want to show you a material. This is actually silicon square net, not an antimony square net, but if you count the electrons, you again see it has 6 electrons per silicon square net. So there's now 2 minus. You go 2 further from silicon, you can get to 6. And this was something I found a while ago, and it actually has these steep band crossings that were verified via ARPUS by us and many other groups often. What we were later more interested is like quantifying this for all materials. So we just didn't want to have one material where you have this type of band structure in a square net, but we wanted to look at all these crystal structures. The square nets are reported and understand when do we have delocalized bonds in these square nets, and are all the ones when we have delocalized bonds then topological semimetals, or do they have steep bends, or is there contradiction? And then the other question is like what is the fraction of the materials that many of those do not have delocalized bonds? Is there like a simple way how we can understand when we will have such a delocalized bonds compared to when we won't, and therefore just from looking at crystal structure predict band structure without doing DFT? That was the goal. So we started with the most simple structure type here, but if you look in a database, you know, there's this databases, this lists all the materials that have been made, really, really great resources. So the inorganic crystal structure database cites more than 500 compounds only in this crystal structure. And my former postdoc Sebastian Clemens did a lot of work, went through all these compounds. And here you see the elements that consist of each position. So the square net that we're interested about position is a green atom. And so you see right away, a lot of things can sit on this, even d orbital materials, but our model was based on p orbitals, so we're probably more interested in the compounds here. And so first we thought maybe we just like sort out everything with p orbitals and then count if there's 6 electrons, and then it should work, right? The whole argument. But we found out pretty quickly that electron counting isn't that simple in these systems, because then you need to know if this element here, the blue or red one, donates or accepts electrons to the other layer. And sometimes it's just not that obvious because these can be extremely intermetallic. Sorry, do you have a question? No, okay. Sometimes they can be very intermetallic, so it's not really clear if the blue or red one is a donor or an acceptor, and then you cannot really assign the electrons to the green atoms as you wish. Yes?
And why there are so many white elements?
Oh, yeah. Good point. Yeah, those are elements that aren't found in this crystal structure type at all in the database. But yes, a good chemist would now try to make something with indium, for example. Like, why doesn't it exist? Yeah.
And noble elements is because the shell is full.
Yeah, exactly. Noble elements is very difficult to have in compounds anyways, so they will be very unlikely to. Yeah.
Is it really necessary to have all of these 3 colors? So let's say if you have only green and green and red, because it seems that it's a layer, right? If I have the green, which is the square node, the blue remove it, you have red as well. Is it possible to get?
So the square net structures that I showed you here, the other ones are actually more complex than this ones, the ones that exist. So this is already the simplest one with like extra colors. With blue and red. And so this is really just listing the elements that are found on this position, right? Sure, you could, of course, for us right now, we really care only about the green ones, but if we want to count electrons, then these blue and red will be important, right? Yeah, sure.
So I know zero chemistry, so forgive me my silly question.
No.
But if I look at this table, I see there are more elements with red and green on the right. Is there any like physical meaning behind the list?
Yeah, it's a good question. So it seems like this Z element really only wants to use these main group elements. So there's definitely a chemical reason about it, and I'm sure Sebastian would know it because he thought about it much more than I, but I can give you the answer. That the interface here, so it doesn't need to mean that they can swap in the same compound. This is just like what compound exists and which elements can be there. So you would have to look at the tables of compounds to actually see.
And the 2 rows on the bottom, what it means again, the purple one?
These ones?
Yeah.
These are the lanthanides and actinides, and so only these elements only reside on this position. So there aren't any square net materials in this crystal structure, at least where the square net is made by a rare earth or an actinide. Yeah.
Thank you.
Yeah. Okay, so electron counting doesn't work. So we thought about something else what we can do to separate the materials with the delocalized bonds to another. And so the idea we had was, if this is a chemical bond, like really, that is our hypothesis, a delocalized chemical bond that puts these together, then the distance here between those 2 elements needs to be shorter than the distance to the next atom above or below. The reason is that chemical bonding, covalent chemical bonding, always reduces distances, it pulls things together, right? Idea is, okay, these must be closer together than this. If this is not a case, then they actually don't need to bond, and there will be no delocalization. But if this is the case, then they need to bond, and we think there's delocalization. And so to test this, we plotted all these materials in these graphs, and we plot the one distance here, the other distance there. And so you get plots here where the yellow region is where you clearly have a 2D type structure. So the square net is isolated and needs to be bonded to be happy. Or the blue area is a region which is more 3-dimensional. The square nets interact with other atoms, and they don't need to be bonds within the square net layers to be happy. And this green area, I always joke we should have made it a gray area. This is the gray area where either thing can happen a little bit. And so we defined this tolerance factor T, which is said when it's smaller than 1, or actually smaller than 0.95, we can be pretty confident there should be, based on our hypothesis, a chemical bond. And then you list all the compounds here. And so then we counted electrons when possible. So all the gray ones we see, we couldn't count electrons, but when possible, we counted the electron counts on the square net atoms. And you see here in this area where we don't expect the bond, they're always orange or yellow, which means that valence shell is either empty or filled, which means there's no need for chemical bonding, right? So these shouldn't have a closer distance to each other, and it seems to match out really well. And then everything where it's not 0 or 8, and there's need for chemical bonding, falls in this area very nicely. So we see the distance will really separate it out nicely. And then you can look at the band structures of these materials. They're nicely listed by Andre Bernovic for us in topologicalquantumchemistry.com. And you find that these are all semiconductors, or insulators, wide bandgap insulators. And you find that many of these are topological semimetals and materials known. And actually interesting, some of them aren't in the database, but you might know that uranium bitelluride is a topological superconductor people study a lot. And it's very highly correlated, so DFT might not be the best tool to predict something, but it falls in a good area of our plot, which is nice. Yeah, so it's kind of in the gray area, but it's slightly lower one. yeah. Okay. But so yeah, one cool thing is it fitted really well, but actually Andre's database already predicts all these things to be topological, so we couldn't really find a new material here. So for that, we went to this more complicated crystal structure type. In this type, the colors now represent something different in our plot. So again, we looked at the band structures in this database, and whenever the band structure showed this motif that our tight binding model put out from square net, we could find it somewhere, we gave it a green dot. Then you see all these are here in the yellow, maybe sometimes in the gray area, but all in the right area. Whenever this had an obvious band gap, we gave it a red dot. Then if they're not listed in Andre's database, they're gray. And so you see all these candidates you can discover here now. And then very interestingly are these blue ones actually, because those ones are materials that in Andre's database, which is based on PBE DFT, very simple DFT, those are metals, often topological metals. But then if you just go to Google and you type whatever formula this is, let's say barium, manganese, fluorine, antimony into Google, with the word band gap, you will find an experimentally measured band gap for these compounds. So I found this was awesome because look at all these blue points. These are points, there are extremely simple rules. You just measure the bond distance, right? It's better than PBE-based DFT to predict the band structure, right? We accurately predict these need to have band gaps, and they do, but DFT actually underestimates band gaps so severely that it puts it incorrectly. And then there's this orange point here, which is where there's no experimental data available. So Andre predicts this to be a topological semimetal based on DFT. Somebody needs to make it to prove to me that this doesn't have a band gap. I predict it to have a band gap. But nobody did. Okay, so then once we really well understood that, I just want to show one slide what you then can do once you understood the system so well, you can go to the real complex materials and see if you find cool properties. So with that, we were interested in these rare earth tritellurides because they have square nets too, and they have a van der Waals gap between two square nets, so you can exfoliate them, or you hope at least at the point you can. And then they have rare earths, which means that they usually should order magnetically. So we were hoping this could be a high mobility exfoliatable magnet, right? High mobility because we know whenever the square net falls in our yellow area, it should have high mobility. Magnetism because of the rare earth, exfoliatable because of the band gap. So you can put these materials in our plot. There's also an even more complicated analog of this, and they kind of all are in that area. But then you look at the band structure, it's actually a mess because the crystal structure gets really complex. Okay, you see this kind of square net bands here, but Fermi level isn't really at the best place because you have a little bit more than 6 of electrons per atoms. You have steep bands, so high mobility is still likely. But if you would look at the database and you see the band structure of this, how many of you would actually go and think this material is interesting to make and study? It looks like crap, right? So, and that's why I say sometimes chemistry is powerful, because we thought it's so worth looking. And so one reason though, we were a little bit worried is because it has these extra electrons, what is actually already known in the literature about these is that they undergo charge density waves. So they're stored, and it's because they have to not exact 6 electrons. And so I was a little bit worried that we fall into this regime where everything is boring and we don't have a hypervalent delocalized bond anymore, and also our high mobility goes away. However, lucky for us, the crystal structure was published of these distorted materials. They get really complex, as you see here. They don't just distort through like very localized bonds that matches the electron counting. So there's still a lot of potential here for delocalized bonding along these kind of patterns. So we decided to just give it a try. After all, I talked a lot about now how we think, but we are still an experimental group. So at some point, you just got to do the experiment. My former postdoc Ximing Lei grew the crystals, so you can grow them really nicely. You see here, really nice square centimeter sized crystals grow out of those. They're very layered, as you see in the SEM. And then if you measure the mobility with the Hall effect, you get a shockingly high number, depending if you fit resistivity or conductivity. It varies a little bit, so let's get with the conservative number here. This is actually, to the best of my knowledge, the highest that have ever been measured in a layered magnetic material. Graphene is higher than this, like phosphorus is on par, and we couldn't find anything else that surpasses this mobility. So therefore, I might argue that the chemistry logic still works, even if the band structure makes you want to run away. Okay, so I wanted to go away from square nets and briefly talk about linear chains, because those also were predicted to have these delocalized bonds, right? So another system where you could look for hypervalent bonding. Here you need 7 electrons per systems now for it, and I won't walk you through it again why it has to be hypervalent. Just trust me on it. If you want to read more paper, he explains it really nicely. But our question was, okay, can we do the same kind of trick with linear chains? But with linear chains, it's actually, with linear chains, it's actually not that simple. So I again went to a physics friend to give a talk actually in the school also, I think Wednesday, and ask her what happens if you put p orbitals, this is just pz orbitals because it's 7 electrons on a linear chain. What's the band structure? Do I get something topological? You shouldn't be surprised. No, you really don't. You get something very unsurprising. It's not topological. It has very steep bends, of course, along the chain direction, and then it has a flat bend, and we'll talk about if this flat bend is any interesting later. Along the directions across the chains are not that great. But then Raquel, who made the model, pointed out to us that if you put 2 of these chains in the crystal structure and you let them slightly talk to each other, then you actually get a topological band crossing as a result of this. Okay, so we again can have this delocalized topological crossing. And I was very happy when I heard this because, you know, I'm a chemist, I make materials, and I just gave you a big spiel about how the complicated band structure shouldn't run away. But because usually the beta of my existence is that you physicists always tell me this is too complex, please make it more simple. It was the first time a physicist told me make it more complicated. And I said, yes, I can do that, you know. So, okay, great. So Jason, a postdoc in my group, then did a great job of identifying materials where you have 2 of these linear chains with the correct electron counts. So here you have bismuth, and the bismuth has 7 electrons, or it can be antimony too, in the crystal structure, and forms these linear chains. But also you see there's all this other stuff, and in this case it's actually kind of important. We cannot really reduce the system only to the chain. So just want to point out that bismuth also plays part in these octahedra here that you see here. That are also going to be relevant. So if you calculate a band structure now of lanthanum, so the metal is usually zirconium or hafnium. This is, oh, sorry, I forgot this. There are actually lots of these materials. Sorry, this is a map where we plot here are the rare earths and here the other elements plotted. And all the points represent a material that exists in this crystal structure. In the yellow regions, it crystallizes in this 2-chain crystal structure. In the blue region, it doesn't. We found those, or Jason found those compounds to be new. We think there's another area to discover new compounds, but there's also a lot of compounds to be studied with this crystal structure and the linear chain. Yeah?
Spin-orbit coupling is important here.
Yes, I will get to that. Very important. Yes. Okay. So because they have bismuth.
Oh,
yeah.
Question.
Yeah.
Sorry, I'm trying to understand. So when you said on the previous slide that it becomes topological, could you define topological material in this context?
So here you get a band crossing which carries a band inversion in the plot here. So this is a topological band crossing.
If it has this band inversion, it's topological. If it's not, then it's not topological.
Yes, exactly. You need to count the number of band inversions to classify further, but yeah, in general, you can make this approximation.
Thanks.
Yeah. Okay, so we have lots of compounds to study. We started with this LN5, MB5, BI5, and NP95 compound. And so here's a band structure without spin orbit coupling of such a compound. And here's the comparison to the model. It doesn't really look that great, you know. So this time the model doesn't really seem to capture it. Although then we look closer and we saw, okay, here this area, which is shaded red, kind of looks like the model. And then this area, which is shaded blue, really doesn't. But if you do partial band contributions, you will actually see that this comes from bismuth orbitals, which are in the chains, whereas this part of the band structure comes from bismuth orbitals, which are in octahedra. Okay, so the bismuth octahedra play a significant role of this part of the band structure, but the chain structure is still. And so now the cool thing happens. So this looks bad, yeah, but the cool thing happens now if you account for spin orbit coupling. Now the band structure changes significantly. Let me go back and forth so you can see it. This is that. Very different band structure. Spin orbit coupling is massive in this compound. And so again, if you highlight the areas here, you see that the chain area is still kind of there. Here are the steep ends, here's the crossing that is predicted. And then now the bismuth octahedra area, this other area, is gapped. So here in this particular band structure, this touches the Fermi level a little bit. If you tune with other materials, you can have this completely gapped here. This is actually topological gap opening, but also it means that in the transport, we can actually anticipate the chains to dominate the transport because there is a gap in this area. So if you look at the Fermi surface, you see that this size, these little speckles which come from this band dipping in here, is a very one-dimensional Fermi surface, right? So it really electronically behaves like the Monty chain. Yeah.
Can you go back? There is a crossing at the edge, which it seems it's absent in there.
Oh, it's there, but it's a little bit convoluted with other stuff that's here.
No, at the edge.
Edge. You mean this? No.
Yes.
Oh, it's the H point. Yes, it is actually, it gets removed by the spin orbit coupling. Yeah. Yeah. So you actually split orbits. You see also how you double the number of bands here from here to here with spin orbit coupling, it splits them all. And it splits them really widely. So it also kind of looks like spin orbit coupling would flatten the band, talking about flat bands, right? And this is because it's okay. So let's go to the Fermi surface here, very one-dimensional Fermi surface. So I just want to show you one slide, our transport studies, and those are still ongoing. But in transport, this is the anisotropy ratio. This was measured by Bingjing and Poinong's lab. And you see that the anisotropy actually kind of shoots up when you go to lower temperatures, really indicating pretty one-dimensional, low-dimensional transport in the system. And so I found it was kind of cool because it started from this easy idea of thinking about linear chains, going to a really, really complicated crystal structure, and then reducing it very simple to a one-dimensional problem again. Okay, so but now I actually want to talk about flat bands for a little bit. And so we saw there was a flat band just in the system, but I get to this in a second why I didn't discuss it in this context. We learned so far that delocalization of electrons causes steep bands and high mobility, so the opposite of flat bands, right? So we could now think, okay, does localization then cause flat bands? And so no, it doesn't. It just makes a band gap, and then bands can be pretty steep above and below the band gap. Okay, the band gap. You could think that the non-bonding interaction that I had before causes flat bands, and that is what happens in the chain compounds. The chain don't really talk to each other along some direction, so it's kind of a non-bonding interaction there. You get a flat band, and that's kind of a boring flat band. There's no communication, so it just is like an atomic insulator, right? It's not a correlated flat band. So in order to have interesting flat bands, as we say, you need a constant amount of interactions in K, and so we say we need forced localization through bonding, if you want to put it in a chemical bonding system context. And I show you on the next slide what I mean with this. This is the work of Milena, a postdoc in my group, and so she looked into this Kagome lattice. And you might be familiar with the band structure of the Kagome lattice on a tight binding level, that it has this really, really, really beautiful flat band, at least on a tight binding level. So we had two questions here. This one was chemically, and actually the chemistry question was already answered by Robert Hoffman again, but we have the chemistry question, why is this flat band there from a chemical bonding concept, and can we learn from this from other questions? I'll tell you in a second why. And the other questions we had that bugged us is like, there's so many materials of carbonate lattices, but not many of them actually have this band structure. And why is that? And can we understand when this type of band structure appears in a lattice and when it doesn't? So here's the first chemical question. So here's how you would draw the orbitals, the trigonal fragment orbital of a carbonate lattice. And so you can see, if you remember, like our picture drawing band structure, when we move up a K, we start creating node here. So we would flip one of these orbitals over. And so this green orbital here would slowly become more anti-bonding and it forms this band. And then the purple orbital here, you have, again, your complete anti-bonding interaction to start with. But then if you flip one of these, it becomes more bonding and you move down. And then this one, this is the interesting one. And you can kind of see it. You have different sized lobes of the orbitals. And so you have kind of bonding interactions, but it isn't perfect overlap. And if you start flipping them, it actually doesn't change how they overlap. So you can do this whatever you want. So this band has to be flat. And so this is a flat band that exists, although there is chemical bonding. So this is not a non-bonding interaction. Okay, that's what makes this flat band so interesting. Okay, but now the other question: why are there so many carbonate compounds and so many of band structures like this? This is a carbonate compound. This is a carbonate compound. There's no carbonate bands in this. This is actually the nicest carbonate compound out there. Cobalt tin is pretty famous. Here are the carbonate bands, and not as nice as in the tight binding model, right? And bands they're kind of flat, but they're not really flat anymore. So what's going on here? How can we understand this? So Milena started looking into these compounds. And the first thing she realized, okay, we need to separate all the carbonate compounds in two big families. One we call linked carbonate lattices. And these are lattices where you have a chemically similar element next to the carbonate layer. So here's the carbonate layer in plane, but above and below, the element is chemically similar. So in order to have carbonate bands, you need bonding within the plane with any orbital. But if there's something chemically similar above or below, it will mess with it. Like the orbitals from here will start interacting with the plane. Or you have separated carbonate lattices, and there you have something else in between, and then you have a chance to have carbonate bands. So the first thing you need to do is you need to toss out all these linked compounds. And then if you focus on the separated one, then you can define a tolerance factor similar as we did with the square nets. And we can say if this is very far away, so the tolerance factor is small, they're isolated, and there really is a carbonate layer, and you should have nice carbonate bonds here. Then there will be an intermediate region different to the square nets, where the T factor is somewhat small, but not too small. And here you will have interactions for the layers, but because the elements are chemically different, you still have a chance for carbonate bands to be here. And I'll tell you later exactly how to get those. And then if your tolerance factor gets too big, larger than 1.4, no chance for carbonate bands. These are too close here. There's no bonding between those. And they're really separated. So let's see how this works out with the data set. So Milena, actually, she did a complete search. So she wrote a code that detected carbonate lattices in all materials that are in the ICC. So we didn't only focus on space group that's usually host those, such as certain structure type. We really went for everything. If you look how many carbonate compounds are there, she found about 3,500 compounds, and then a few that we called molecular compounds. So these are very boring type of flat bands that we didn't consider them, and then some where we couldn't find a band structure for. So those were topped out of the data set, but this is the big data set. Then the first thing was separating them with linked and separated lattices. You see, unfortunately, the vast majority of these compounds is linked, so they're already all out of the picture for having carbonate bands. And then you separate those ones which have a potential further out. And I show you here what they mean. So again, Milena looked at all the published band structures. And so she labeled those and plots later with the circle, which have clean carbonate bands. And these also have clean carbonate bands, but you have like large unit cells that fold over each other. So you have a lot of carbonate bands in this. Then a few compounds, not many, have carbonate bands very far away from the Fermi level. And then sadly, vast majority again has no carbonate bands of these materials, and they're labeled with a triangle. So when I show you now these plots, similar for the square net, the only thing I want you to remember is the triangle is bad, and all the other symbols are kind of a good sign for carbonate bands. Yeah.
These are still some flat bands, right? In the green part.
Oh yeah, this is coincidence. This is just like a cartoon bank structure of no Kagome bands. It doesn't mean anything. So. Okay, so now this is a plot for space group R3 bar M, which shows a lot of Kagome materials. Here you see the 3 areas. Here's the tolerance factor is large, where we don't expect any Kagome bands. And you see with this one example I talk about a second, we have only triangles here. And then here in these 2 other regions, we only have good symbols. Okay, so the tolerance factor against the distance is separated out pretty nicely. Here, those ones, these are compounds which are actually spin liquids, quantum spin liquids. So it's again, these are compounds where DFT predicts very, very pretty Kagome bands, but experimentalists have made these compounds and they're very insulating. So this is again, you see how these plots actually often do a better job than DFT. And then you can do this with another space group. And again, triangles are only up here, other symbols are here. Another space group, same story, triangles only here, other symbols only down here. And again, these circles that fall in the wrong area are quantum spin liquid materials where we don't really trust the DFT. So here again, we can use this pretty easily to separate out the materials. But I want to show you, sadly, there's one sad aspect about this story. Although it works so well, I want to show you these materials, band structures, which we labeled as nice Kagome bands, just a little bit to show you. So here's one. This has a square, which means there's several Kagome letters in the layer, and it's therefore you get a lot of bands. These are Kagome bands, it's just not pretty. And you can understand why. Because if you look at like just constructing this from fragment orbitals, you see what makes up the Kagome bands is always the D block elements, and they just overlap like crazy. There's too many bands, and so you get this messy bands. And so Milena also made periodic tables up here where she plots all the elements that can sit on the Kagome lattice, and you see they basically always are D electron elements that makes up these bands. So you will very likely get a messy band structure.
You said that you have hundreds of them, which is circle, which is isolated.
Yeah.
Right?
Yeah.
Do you have a band structure? Yeah.
Yes, this one. This one has a circle, but it has a non-ideal tolerance factor. And you see the Kagome bands are here nicely. Here's a crossing. Here's a semi-flat band. But still, it's not. It's like right. Cobalt tin, but I showed earlier, also is a circle, right? This means that. And so here you see though why this intermediate tolerance factor can still tolerate Kagome bands, because as long as you have trigonal fragment orbitals left that can bond in the plane, and I don't want to bond with the atoms above and below, then it's possible that they form Kagome bands. And here in this case, the atom which sits very closely to these layers likes to bond to itself through it. So as you see here, the mixture from these blue elements in this band is minimal. So you can have Kagome bands, but of course never perfect. And again, you see even here for all these intermediate tolerance factor compounds, Kagome atom is basically always a d electron atom. So the band structures will always be this kind of convoluted. Here's an example. I just wanted to show you about how messy it is. I don't know if you're aware of this. Is a very famous Kagome compound. This is the band structure, it's a complete mess, but people study it for their Kagome properties. It falls in the intermediate tolerance factor range where there's some interaction with the layers, and there are Kagome bands hidden here, but very hard to see. And so lastly, I just want to show you where the elements can sit in Kagome materials if they don't have Kagome bands. I'll explain you the reason later. But what is interesting is like whenever you have something here in the periodic table where you don't have d electrons, so the purple ones are Kagome atoms again. There won't be Kagome bands for certain reasons. So unfortunately, whenever the tolerance factor is small, we have them only here in the D block. When the tolerance factor is large, we have them everywhere over the periodic table. And so here, you don't get Kagome bands because the Kagome lattice is always either formed by a cation, so there's no electrons left in the Kagome plane to form bonds like Kagome bands, or it's formed by a happy anion, filled valence shell, also no desire to form Kagome bonds, or it is so strongly connected to the atoms above and below, so that the Kagome bands will be completely destroyed. So with this, we can sum up this part and say, how can we get, this is a flow chart, of how can we get nice Kagome bands in the material? So the first question, the first one, the first thing you ask yourself when you have a compound is there a cargomere lattice? And if there is one, then you ask, is the cargomere lattice linked? Because it should not be linked. Okay, you can toss it out right away. If it's not linked, then you ask yourself different questions. What's the tolerance factor? If it's really large, no chance for the cargomere bands. If it's very small, very good chance for cargomere bands, everything great. And if it's into the intermediate range, you think about factors like electronegativity difference. If it's large, then it's more likely that the close by atoms will interact with each other more than with the cargomere bands, and you have a better chance for cargomere bands. So this is how you can sort them out. Here's the electronegativity difference. Okay, and so with this, I'm basically at an end. I just briefly want to talk about the flatband database because this is a flatband school, and we only contributed very minor to this paper. So this is mostly Andre Benedict and Nicola Rignol's work. And so I hope, because both of them will be speakers in the school, maybe one of them will discuss this in more detail. But I want to point out that they did a mammoth kind of work of really listing all materials that have flat bands, some kind of flat bands in this database that you can find under this ID here, materials flat band database, and that they separated them in 3 different kinds, where like the topological, atomic, and obstructive atomic, and the atomic ones are basically the boring ones that we have, the non-bonding ones, and the other ones are the interesting ones. And so I just want to give you some statistics of it, because I think this is chemically interesting, is that they found, out of 28,000 materials, they found 2,400 where you have some portion of a band somewhere flat. But only 345 are good flat bands, you know, where it looks like. So flat bands are pretty rare. Yeah. And this doesn't necessarily mean that they're interesting flat bands. More than 50% of the compounds with flat bands are cargomere compounds. So the cargomere lattice is very special in creating these kind of interesting compounds. Some other good lattices are pyrochlore, which is a 3D version of a cargomere. So we've tossed them out because pyrochlore was classified as linked, but it might be interesting to look for other kind of flat bands and pyrochlore lattices in the future. Leaf lattice is also a good lattice if you have it for flat bands. And then they did find, though, some very interesting compounds in this list. So I want to just show you one of them so that you look at the complete list yourself. But this is tungsten oxide, which is a material which has been studied actually a lot, and it becomes superconducting actually really easily if you intercalate something into this. And interestingly, it has really nice flat bands here, and it's not a cargomere material. So just wanted to close on that. So to sum up, I hope I could convince you that chemical rules can be extremely useful to predict materials, band structures, and properties, and very simple effect of doing it. And we did this in several ways. We did this in square nets to predict high mobility in materials. We did this in linear chains to find interesting one-dimensional compounds. And we found rules for cargomere materials to separate out when we can have these types of bands and when we can have not. With this, I want to thank you for your attention. Thank my amazing, wonderful group who is here and does actually all the work. Lots of really good collaborators who help us through this too, and also all the funding, especially PSSCMP, of course, in the Mercer. Right. And then I thank you.
Thank you for the great talk. And yeah, personally, I do find the chemist perspective very inspiring.
Thank you.
So let's take some questions.
So to talk, I just have a really basic questions. You mentioned a lot about localization. I wonder what exactly localization means in this context.
Yeah. Oh, good point. Yeah, good point. There's probably also difference in chemistry. So in chemistry, we say a bond is localized when it's either an ionic bond, so your electron will completely sit at the anion and not at the cation, right? Or it is a very strong covalent bond, which means 2 electrons are shared between 2 atoms, like in a hydrogen molecule, but they don't really move and jump along the other atoms. So diamond is a case like that, right? So this is
another question is, yes, we mentioned about band inversion. I heard this term a lot. This kind of question when you talk about this. Does that imply there's a natural order of bands, like S would be the highest, and then P, then D? That any change of that order will be a band inversion? Is that how it's defined?
No, it is mostly defined that the bands, like with a continuous irreducible representation or orbital character for chemist is more easy to think about this, but of course, correct is more in thinking about in terms of symmetry and IRIPs. If they cross in momentum space, but they keep their area plane crossing, right? So it's not an avoided crossing where they gap, but they invert their current.
Yes,
Yeah.
About this coordinate materials, is it possible to do a proximity effect on them, like proximity superconductivity, proximity magnetism?
Yeah. So the thing is, when you sure, I mean, I guess you could take a bulk material and then deposit a superconductor. That should be possible if you want to have.
Or even so that some of them can be exfoliated,
Yeah.
so you can have probably thin layers.
Yes, exactly. I just want to show you. So monolayer of this structure is this unit, right? So it's not, but yeah, you can get to a monolayer here.
My question is, what protects the delocalized bonds in graphene from sort of spirals or capillary deformation from chemist's point of view?
This is a very good question. Chemists have discussed about this a lot, and I haven't found a really satisfying answer, to be honest. But what I can tell you is that they really did models of like how many benzene rings do you need to condense when they stop distorting, right? Because okay, but it's a single benzene doesn't distort, but then two benzene rings to each other, they distort. So there's a molecule called naphthalene, and then three of them still distort. And then if you make a chain and you make, I think you don't need much, like 4 or 5 in this direction and a ribbon, and they won't distort anymore. But yeah, so the concept that the chemists say is called aromaticity, and it's a little bit unsatisfying. They say if something is aromatic, it wants to be delocalized. If it's not, it doesn't. And there are rules of when something is aromatic, when it doesn't. So, but that's basically what it is.
Thank you. And the related question, you explained hydrogen molecule via this spirals deformation in a chain, right? And why doesn't the same work for other elements of the first group, which are metals? What is the principle?
Oh, why they don't want to do a Pius distortion? Interesting. I guess why they don't want to form molecules, right? Well, I guess they're too big. That's the easy answer. So they prefer to form ions and lattices. It's something called polarizability. That there's an electron cloud in a, like, hydrogen has only a proton in its nucleus once you take the electron out, right? And if you go to lithium or sodium, you already have some electrons around the nucleus too, if you only consider the valence shell. And so those can react with electric fields of other ions, so it's much more favorable to form a lattice.
Thank you.
Thanks for the great talk. When you said the GFT prediction was wrong, did you falsify it by actually doing an experiment, or there's a better numerical scheme out there?
So I found out that it's wrong by looking up existing experiments that are published.
I see.
But you can, of course, repeat the DFT calculation with a hydrogen functional, and you will also get a gap. If you didn't do it for all of them, but I think we did meta GGA and for like 1 or 2, and we found a gap in this situation.
Okay, thank you.
Okay, we have one question from webinar. I guess it's in this slide. What is the difference between the 2D and 3D band structure in this one?
Oh, so this is the difference of this is the distances. So when we just label a 2D here in this case, these are very isolated. The bonds here are shorter than the bonds to the next one. So in this area, this is basically really a isolated 2D square net. And here in this area, it's more 3D because then these are very close to the next atom. So you shouldn't draw it like you should draw the bond to the next atom.
You showed some very interesting plots of cognate band structures for cognate materials. Are there any examples of a crystal with isolated cognate bands near the Fermi level?
No, I mean this is the best one basically out there. There are some where they turn out to be quantum spin liquid, where it looks like it, but then they're very insulating. And then there are some where it's near the Fermi, like in some organic complexes. I think you can discuss with Milena, she knows better after, but there are some where you have nice Kagome bands near the Fermi level, but they're filled still, so it would be hard to access them. Maybe you can with gating, but it's actually very difficult to get them to.
Thank you.
I don't have a question. So follow up the last question. Can we do something to isolate the different band? Let's say if you exfoliate this material and you apply displacement field.
Yeah, I mean, I guess if you find a good one and you can exfoliate and gate it, then you have a chance. Chemically doping, I think it's difficult. But with organic materials, exfoliation is sometimes challenging. Maybe you can grow a film. That's something so we found the nice Kagome bands in more like metal organic materials. So I'm the wrong chemist to ask you of like how easy it would be to gate it. But yeah, I don't think it's impossible. Yeah.
Okay, if there are no more questions, let's thank Professor Schoop again.